This is recitation 7, and today we will work with time-independent simple circuits, which means that we close the switch in our circuit, we wait for a long time. When we reach steady state situation, which means that all currents and current densities J, currents I and current densities J that do not depend on time. So they are constant with respect to time. Okay, so we will need several formulas today to describe the circuits. And first of all, I will write the law integral E dot dr over closed loop is 0. Because it is steady state situation, this equation still works. The second equation that we will use is integral J current density dot ds, which means that flux of a current density out of closed surface is 0. And this works again because of steady state. Current and current density do not depend on time, so amount of charge that comes to some cross-sectional area should be the same as amount of charge that leaves this cross-sectional area, so closed surface, a flux of the closed surface is 0. We need one more equation. We need difference in electric potential V at R2 minus V at R1. I remind you, this equation we already worked with it, and it still works because of steady state. It's minus integral from R1 to R2 E dot dr. Again, if I consider closed loop, then it is 0, but we understand this relationship. And I want to draw your attention that to the fact that V at R2 minus V at R1, if I take absolute value, let's call it delta V absolute value. Absolute value of delta V is equal to absolute value integral from R1 to R2 E dot dr. And this minus means that if I consider E dot dr around the loop, it will have opposite sign to difference in the electric potential, or sign in voltage. Two more formulas that I need to remind you about. So we will work with batteries, and we will denote voltage across battery as V. We will work with resistors. We will denote them as R. And I remind you about Ohm's law. According to Ohm's law, the difference in voltage across the resistor delta V is IR, because R is V over I. And if I write a V at R2 minus V at R1, let's call this point 2 and this point 1. So I write V at R2 minus V at R1 across this resistor. Length of this resistor, let's call it L. I have it as minus integral from R1 to R2 E electric field. If current is in this direction, then electric field that is rho J, another form of Ohm's law. E is rho resistivity J. Electric field is also to the right, so what I have here, E dr, or it is minus E is constant, and R2 minus R1 is just length of this resistor. In other words, difference in voltage across the resistor is negative, or voltage drops in the direction of current flow. Our current is to the right, electric field rho J is to the right, and voltage here is higher than voltage at point 2. That's what we need to know about the resistors. And now let's talk about capacitors. So I'll consider a capacitor, capacitance C, and if I charge this capacitor with a battery of voltage V, I need to indicate the charge. Let this be plus Q and let this be minus Q. Then what will be, this is V, plus minus, what will be voltage change across the capacitor? C, capacitance, by definition, is Q divided by delta V absolute value, or delta V across the capacitor magnitude. Delta V is Q over C. And I believe I summarized all formulas that we need to use to solve any problem with circuits. Now let's apply these formulas to the simplest situation possible. I have a resistor, resistance R, and I connect this resistor to a battery with voltage V. This is positive terminal and this is negative terminal of the battery. What I want to find? I want to find current in this circuit. Well, we know what is current. Those are ideal wires. So if I have, I have change of voltage across this resistor as V, it is given, then current I will be just V over R. We know this. Ohm's law, simple situation. But we will work with more complicated circuits. And I want to use these simplest circuits to apply several steps that we will later use for more complicated circuits. What are these steps? Well, when you start any problem with circuit, first of all, you indicate which law you use. Those are two laws that we will use when we work with circuits, steady state situation or time independent circuits. Law, then next step, direction of current. Let's call it 1. Direction of current. What is the direction of current? Choose something reasonable. In this case, it's obvious choice. Current is in this direction. Then, next step is to choose in which direction you will go around the loop. You need the loop, you go around the loop. So which direction will we go around the loop? Let's go in a clockwise direction. This indicates my DR, direction of DR. I go around the loop in this direction. So direction in which you go around the loop, or I will call it direction of DR. Okay, so next, I need to indicate charges on the capacitors. If I have a capacitor, no capacitors here, we can charges, did I spell it right? On a capacitor, if you have a capacitor. In this case, we definitely skip this step. And then you start applying these equations. So there are two different ways to think about this circuit. One of these ways is to go around the loop in terms of delta V, because we understand that delta V, magnitude of delta V is the same as magnitude of E dot dr. So my equation is delta V across this loop is 0. I start with the battery. From minus to plus, I have positive change. I remind you, I go in this direction. For me, it is to the left. What about you? Is it to the left? Okay, we need to cut it. I apologize. So this part. For me, it is to the left. From minus to plus, I have positive change in voltage. That's why I put plus here. And magnitude of change of voltage is V. Now we keep going. This is ideal wire. Now we come here. This is my current. Remember that voltage drops in the direction of current flow. We just proved it. So the change of voltage across this resistor will be negative. That's why I put minus. The magnitude of change of voltage across the resistor is IR. So I put IR. And we don't have any other elements in this circuit. So this is 0. And of course, I get the same answer, the same as we expected. I is V over R. That follows from this equation. Okay. So this is one way to think about this problem, to go around the loop in terms of delta V. Now, Now, I will teach you another way to think about this equation. We will go now around the loop in terms of E dot dr. Why am I doing that? Because later, in 2 weeks, we will add non-zero right-hand side of this equation. And it will be so much easier when we have non-zero right-hand side, when we will have Faraday's law, changing flux of the magnetic field here on the right-hand side of this equation. It will be much easier to understand it in terms of E dot dr. That's why all problems that I will be solving, they will be in terms of E dot dr. So let's solve this problem in terms of E dot dr. I indicate the law. The law is integral E dot dr is 0. We understand that this is the same as this with respect to different signs. All signs here will be, for delta V, will be opposite to the signs of E dot dr. I start here with the battery. From minus to plus, I have positive change in voltage, which means negative change in E dot dr. That's why I put minus for the sign. Magnitude is V. We keep going. Now I come to this resistor. Current flows to the right, which means that current density J is to the right, which means that electric field E, which is rho J, is to the right. This is my electric field. And dr is to the right. So we have electric field to the right, dr to the right, which means dot product E dot dr positive. That's why I put plus here. What is the magnitude of E dot dr across the resistor? Across this resistor, magnitude is IR, so it is minus V plus IR, and this is equal to 0. Of course, the answer is the same, just all signs in this equation are opposite. So current is V over R, problem solved. Now we will add one more element to this circuit. We will still have a resistor, we will still have the same battery, plus and minus, voltage V, resistance R, but I will add a capacitor, capacitance C. R is given, C is given, V is given. What I'm looking for? I'm looking for current in this circuit, and I'm looking for the charges on the plates of the capacitor. Okay, we follow the steps. Law, I have integral E dot dr equal to 0. Then I need to choose the direction of current. I have plus terminal here, so reasonable choice is to choose current flowing in this direction. Then next step, I need direction of dr. So let's go in clockwise direction again. This is the direction in which I go around the loop. Charges on the capacitor, we need to choose something and stay with our choice, something reasonable. So I will choose plus Q and minus Q. Now let's think about this system. So at time moment 0, I closed the switch. There was current and capacitor was charging. But we will understand this process later. At this point, what we do, we wait for a long time. When current does not depend on time, it's time independent simple circuit. So if current does not depend on time, if you waited for a long time, what happens? Capacitor was charged up to its capacitance with charges plus Q and minus Q on its plates. And if I keep non-zero current, then what will happen? This current will be coming and coming and coming and will be charging and charging this capacitor. And eventually this charge will go to infinity. I will build infinitely large charge here, which is impossible. Which means that in steady state situation, current through a capacitor is 0. In steady state situation, current through the capacitor is 0. So this current is 0, no current. Okay, now I will write E dot dr across each of these elements of this circuit. I go in clockwise direction across the battery. If I go in this direction, according to my choice, from minus to plus, I have positive change in voltage, which means negative change in E dot dr. That's why I put minus. Magnitude is V. We keep going. Current is 0, as we just found. Then what is E dot dr across this resistor? E dot dr across this resistor is IR. If current is 0, then it is 0. So I have 0 E dot dr across the resistor. Then with my choice of positive and negative plates, I have electric field to the right from plus to minus. This is the direction of the electric field. Electric field is to the right. dr is to the right according to our choice. They're in the same direction. Dot product is positive. That's why I put plus when I find voltage change across this capacitor. What is the magnitude? The magnitude is Q over C plus Q over C. And there is no other elements in this circuit. We come back to the battery, we close the loop, it is 0. What is Q? Q from this equation is C times V. Now I will change my circuit again. This time I will have a resistor R1, then I will have a resistor R2, and then I will have a resistor R3. And this is the case when we need this equation integral J dot ds. Well, I will connect it to the battery, we will have closed loop, everything. What I want to show is that when the situation when I need this equation. So if I have current I flowing through this resistor, this current I comes to this junction, and this is steady state. So I have continuity equation. I have current that is flowing into this junction. It has to be equal to the current that is flowing out. So let's call this I1 for consistency, then I2 and I3. I have currents coming out, which means that current I1 that is flowing into the junction is equal to the sum of I2 and I3 that are flowing out of this junction. Continuity equation. So in addition to E dot dr, when we do our loops, we will have one more equation, continuity equation for the junction.